Hello again, this is Skip McCauley, Victor Echo 6 Bravo Golf Tango. This video presentation is going to show you the struggle I had getting high power for 6 centimeters for my EME operation. My first attempt at getting on 6 centimeters was that I bought two of these nice looking amplifiers off of eBay. These two amplifier modules were capable of putting out 20 watts each, and with a little bit of tinkering, I hooked up the wires and had controlled bias on it and had them powered up. They, with a little bit of snowflaking, they worked well. Take note of the wires I have soldered onto the modules are for testing and how close they are to the 110 volt AC receptacle plug on the bench there. You can guess what happened. One of the wires, sure enough, went right into the receptacle and saw a large flash and vaporized the foil right off the board, plus did in the output device of this amplifier. Needless to say, I was fairly ticked off and decided there had to be a better way. What I wanted preferably was an amplifier that I could build myself and also have parts that were easily available. On the web I found a great presentation by Hans, Sugar Mike 6 Papa Golf Papa, on these experiments he was doing with GAN devices for 5.76 gigahertz amplifiers. He had done some in-depth experimentation with these GAN devices and exceeded their ratings and proved that they could be used as a good amateur amplifier. With two GAN devices working in parallel, he was getting 100 watts. Well, I was sold. This is just exactly what I was looking for. I got in contact with Hans and he helped me out immensely. He sent me PDF files for board layouts, schematics, etc., and I proceeded in building a 100 watt amplifier. Hans also designed a very nice bias circuit which had good protection for the GAN devices also. First was to build a 12 watt driver amplifier to learn some new skills. New circuit boards had to be built using Rogers' special circuit board material, which was a trick because I'm used to using ordinary copper board that's light sensitive. This stuff isn't. Holes were drilled in certain areas and using solid bus wire was fed through for the ground vias to go from one side to the other. Then on the ground side the wires were cut off almost flush and soldered to the ground plane of the circuit board material. Then these solder pads were sanded down flush onto the copper material itself so that the whole board would lay flat on top of a piece of heatsink material. Next I soldered on all the parts for the bias section only and was hooked up and tested thoroughly before the RF parts were connected. Those parts would come on after the main FET is soldered to the heat spreader. Next I milled out a small aluminum chassis for it and sized up a copper heat spreader to fit into it with the board on top of it. With the RF board bolted down to the copper heat spreader, I scribed a location where the FET was going to be located. Next I surrounded the scribed location with capped on tape and filled the location with a bit of solder. Next a small GAN FET was held in place on top of the solder pad with a specially made clamp to keep pressure on it while it was located on top of a heating strip and waited for the solder to melt. After the solder took, it was removed from the clamp system, the capped on tape was removed, and everything looked good. Now I could bolt the copper heat spreader to the aluminum heatsink chassis, slide the RF board underneath the GAN FETs, and everything looked perfect. Everything was lined up. I soldered the GAN FET tabs onto the board, placed the extra parts for the RF section itself, and proceeded in testing. I first used a signal generator to drive the new unit. Couldn't quite get enough drive out of it, and switched over to the Coons transverter and proceeded in snowflaking. No problem getting a full 12 to 15 watts out of this little unit. So having great success and getting this little amplifier to work and getting a good 12 watts out of it, I was ready to tackle the next part of the project, the 100 watt amplifier. This next part of the project was a lot of fun and a real learning curve. I mentioned earlier that this RF board material from Rogers wasn't light sensitive. I had to import this positive 20 spray to coat them so I can make a board from the positive transparencies. So another device I had to build was a circuit board dryer so that after spraying the boards I could have them dried and ready to use in a matter of minutes instead of 24 hours. It's mainly made of a die cast aluminum box with 4 resistors that ran at 24 volts and created a lot of heat, completely wrapped by styrofoam to hold the heat in. The wet circuit boards just laid on a small tray that was inside the box. Of course, this is a perfect location to add another pick for temperature control on the dryer. Using a positive transparency, the rest of the board was made using the usual UV light for exposure through a developer tank and then into the etchant for developing of the board. This is a picture of the circuit board for the 100 watt amplifier made from the Rogers RT5870 material. It's really different from ordinary FT4 material. It's so soft you can cut it with a knife. This picture shows the 3 boards put together, the 100 watt amplifier in the middle and the 2 bias boards on each side. The soft board of the 100 watt amp is cut in a shape so that the boards fit snug up against it for wire jumpers. The same process was used as the 12 watt driver for connecting the ground connections to the bottom side of the ground plane using solid bus wire. I had to be careful when tapping the bus connections on the far side flat before soldering, because if the punch slipped off, it would go right through the board material because it's so darn soft. Now that I had the circuit boards built, I could use them as a template to guide me for drilling holes. So a copper heat spreader was built, and then that would go on top of a heat sink, which had to be custom made. So the milling machine came into play once again. I took a block of 1-inch aluminum, marked lines on it, and proceeded in milling out fins for the cooling part of the heatsink. Using a 1/4 inch mill end, I went back and forth till I reached a certain depth and continued right across the whole block. Now that the heatsink was finished and the copper heat spreader fit on top of it nicely, I bolted the boards down, and you notice there was a slot cut in the copper heat spreader in the middle, which is going to be for the GaNFETs to fit into. It had to be lowered so that the tabs would lay flat on top of the board material. Next was to get the 2 GaNFETs soldered to the copper heat spreader. The small slot milled into the copper was filled with solder, and then again the capped on tape was surrounded the area that was going to be soldered to. Again, a custom clamp was used to hold the GaNFETs in place. The assembly was set on the heat strip, and as the solder melted, the spring-loaded clamps pushed the FETs down into the slot. Once the copper plate had cooled, the clamps were removed and the capped on tape was removed, and the FETs were nicely in place. The RF board itself was cut in half and cut in special shapes so that the 2 separate boards would slide underneath the tabs of the GaNFETs. Now I could take the 3 boards and bolt them through the copper heat spreader into the aluminum heatsink and finish soldering all the RF parts onto the main board. One thing I forgot to mention earlier is that when I was testing the individual bias boards, one of them didn't work right, and using this Chinese microscope I bought, which is extremely cheap to buy, I was able to find a capacitor that wasn't quite centered between the foils, and there was a path going underneath it that got shorted. It's a great device, but it also shows you just how bad your soldering looks. So the next part of the project was building walls or enclosure for the amplifier using 1/8 inch aluminum plate. The small enclosure walls were made in separate pieces so that they could be removed, just in case if I had to replace a GaNFET, they could be removed, and then the RF boards themselves could be slid sideways off the copper heat spreader to get at the GaNFETs. The whole amplifier unit is mounted on top of 4 aluminum standoffs for mounting, and also a cooling fan is mounted underneath to keep it cool. Finally, came to the testing stage. This is a special test jig I built so that I could use relays to sequence the bias control and the drain voltages so it wouldn't blow things up like I did with the loose wires into the AC receptacle. In this picture you can see the Coons transmitter at the top that feeds into the 12-watt driver module, and then from that module it goes up into the input of the 100-watt amplifier. The output is going off to the right of the screen. This picture shows a little wider view of the testing. 2 ammeters for monitoring the individual GaN-FET currents on the 100-watt amplifier. The output of the amplifier goes to a 20 dB power attenuator, and from there it goes into a power sensor for the HP power meter. So the testing continued, and with snowflaking of the amplifier, I was able to get over 100 watts output from this little device. I was quite pleased. I didn't have any video of it, but I'll make up for that later. So now with the main amplifier parts finished and working, it was time to build the feed assembly. First off though, I needed a feed horn. I did a series of experiments trying 2 different lengths of tubes with the screw polarizers, and then 1 tube with the squeezed section for the polarizing part. Construction of the copper feed was straightforward enough, but it took some doing just to make sure that the holes were square and the threaded holes for the bolts were square with the world also, so things would be straight. When all the metal construction was finished, next was tuning the probes and adjusting the circular polarization bolts for the feeds themselves. I'm not going to get into any detail because I covered all this tuning procedure in another video, and this is getting to be kind of lengthy as it is. Pictured here is the feed assembly that I used. It's mounted on a custom bracket. You can see the isolation relay for the preamp and the hard line that connects to the power amplifier. Next, the main parts were situated on an aluminum plate that would fit the feed mount on the dish, and spots located and bolted down. Getting the RF plumbing with the semi-rigid hard line was fun, getting all those bends to go around things without being kinked. Also building little brackets to hold the semi-rigid line in place so they wouldn't vibrate and bounce all over the place and break off or just come loose. Figuring out where to mount all the hardware is half the fun of these projects, I think. The current sensors, relays, fuse holders, etc. Then the point-to-point wiring and testing as it goes along. And of course, as usual with my projects, there has to be a PIC controller in here. The PIC circuit monitors things such as temperature, GaN-FET current, etc., and sends data back into the shack to the sequencer and also to another Visual Basic screen, which we'll see later. Shown here is this front terminal strip, which is connections to the preamp and the preamp relay. This makes it easy to disconnect and pull the whole feed horn off as a module. The rear terminal strip is the interface between the quick disconnect Amphenol connectors and the rest of the circuitry. It used to be how I hooked it up, but now it's just mainly for troubleshooting. This picture shows you the Tuttle diode detector. It samples the RF and gives me a relative indicator back in the shack of the output. The last part is the what I call the roll bar. It's just a protection cage for the assembly. Easy to carry, and when I wrap plastic around it up in a feed horn, it keeps the plastic off the components. There is a 6-centimeter event coming up in a week's time, so I thought I'd hook things up to check it out and make sure everything works before the contest. In order to test the feed amplifier system, the first thing I had to do was pull the feed horn as assembly module off, which is quite easy to do as I show here. 2 hardline connections and 4 wire connections, and that's all there is. Comes off easy. I had to take the big power supply and reconfigure for 50 volts for this test. This is what this amplifier uses. It was set up for 30 volts for the 9 centimeter feed before. I'm not going to get into detail here because it's shown in another video on my channel. So this video is going to show you the rundown of the testing operation here and how everything's laid out. First on the bench is the 50 volt power supply for the amplifier. Next is a Kenwood radio I use for the IF source. And in front of that is the feed assembly test box. This test box replaces the sequencer and it plugs directly into the feed assembly. From here I can switch different circuits on. I can check the preamp, the isolation relay, and for this example I can control the bias, the GAN fed drain voltages, and the push to talk. It just makes everything so much easier. So continuing along the bench, we finally come to the feed assembly itself. The roll bar has been removed for easy access to the parts. Continuing from this angle, you can see the small chunk of semi-rigid line that comes from the output of the amplifier and connects to the input of the Narda 20 dB attenuator. This small chunk of hard line does get warm. The output of the Narda attenuator is fed into the 3 watt HP power sensor, and that of course goes up to the HP power meter for the final measurement of the output. From there, try and ignore all the junk on the workbench, and we'll swing the camera up to one of the monitors, and this is the Visual Basic display of the diagnostic screen for the amplifier and the feed assembly itself. The next screen is showing the small Visual Basic display, which is the diagnostics for the 50 volt power supply. So with no more delays, it's time for some action. On the Visual Basic screen here on the status part, you'll see how the components of the amplifier come to life as I switch them on. The GAN FET bias is turned on. Next is a GAN FET drain voltage. Then finally I'll switch the push to talk on for transmit. So this is showing you that all the stages of the amplifier are turned on and the transmitter's in transmit mode. You can see up on the 2 top left text windows that the idling current for both GAN FET sections are in play, 0.2 and 0.3 of an amp. The amplifier voltage is at 51.3 volts, and the amplifier temperature is right around 21.9 degrees centigrade, so it's good to go and ready to transmit. I've keyed the Kenwood radio and I'm slowly adjusting the drive to get it up to 100 watts. So I'm switching things off in reverse order, and you'll see it on the status screen. The idling current for the GAN FETs has dropped practically to 0. The cooling fan would stay on, but the temperature is at the shut-off set point, so it goes off. This is a quick video of the power supply status display. I load tested it earlier up to 20 amps, and you can see when it transmits it's only drawing close to 5, so well within spec. This video is going to show why I love putting PIC circuits in these projects. This status screen up to this point has been showing that the sequencer is disabled. It's because we're in this testing mode and there's no sequencer connected, so normally it would be green and showing that it's enabled. Normally the sequencer would switch things on in a specific order, but since I'm using a test box, I can do it any order I want. So just to show what happens, I'm going to switch the transmit on the transverter on, and there's no voltages applied to the amplifier, which would be the same thing as the fuse blown on one of the GAN FET connections. As soon as the PIC circuit senses that the transverter is switched to transmit mode and that there's no voltages applied to the amplifier, it switches into an amplifier voltage alarm and shows you that there's a major fault at the top display. At this point, the sequencer has been disabled and everything's been shut down, and the only way to get it back again was be recycling the power to the feed PIC circuit up top. After I've recycled the power to the PIC circuit, I can switch things back on in the proper order, and everything's good to go. One other display of the Visual Basic layout is this set point adjusting screen. This is where I can go in there and adjust the different temperature set points, high voltage alarms, low voltage alarms set points, etc., etc. Okay, this is when all the fun and effort pays off here in the Echoes Off the Moon. But first, there's a few more things to install and hook up. The first thing I had to do was drag the heavy 30 volt / 50 volt power supply out to the tower stand and hang it up by its hooks on the stand itself. Get the 220 volt power cord strung out to it from my garage. Here we go. Now it's time to get the feed assembly installed, so up the elevator I went, and this is how it's done. What's really nice about these small feeds is that I don't have to lean out past the elevator and bring it in from the front. I can slide the whole assembly in from the back. It fits through the square hole in the frame. So to speed things up a little bit here, I'm going to increase the speed here of the video 2 times. The assembly is slid into the mounting frame. I have some marks on the assembly plate to show me where the best or optimized position is for the feed to the dish. I have a couple of Teflon sliders which go underneath the bolts that clamp the assembly to the frame mount itself. It's very handy to have this remote control box up top there so I can move the dish back and forth to get at different positions on the feed to work on. That horrendous noise was the elevator being lowered. The neighbors love me. What I'm working on now is getting the interface cables between the junction box of the dish up to the quick connect ports on the assembly itself, and then the 2 coax lines over to the heliax cables. Even with these Amphenol quick disconnects, it still takes a while, but believe me, it's a lot easier than hooking all the wires up to that terminal strip on the back side of the feed assembly there. That's how I used to do it. I know somebody's wondering why RG58. Well, the transverter's up here in the assembly, so I'm just using a 144 megahertz IF feed up to it, so line loss is not an issue. The second line is the 10 megahertz reference for the transverter itself, so no line loss, so it's just much easier hooking it up this way. So everything checks out and it's all hooked up. No weather cover, this is just for the demo. So it's time to move it up and away. If anybody's curious, that's a starting of a nice crop of canola growing in the field there. Okay, back in the shack. Doing a quick run past the gear again, showing what's being used for the 6 centimeter operation. Display on the left is the new status display for the feed assembly up top. Now I'll sweep the camera down past the main racks over to the 13 centimeter rack near the bottom, and it's where the 6 and 9 centimeter sequencer is mounted. They share the same sequencer. Okay, we're slowly getting there, eventually. This is the status display for the feed assembly and receive right now, showing the signal paths in green, and as we go to transmit, everything goes red. Okay, being a touchscreen, I hit the power amplifier button and it takes me over to the feed assembly status display. As I key the transmitter, you can see the different display messages come up, and also all the voltages and currents displays at the top. Hitting the setup button, this takes me over to this screen, and this is where I adjust all the different set points. With the keypad, I'm going to change the existing temperature alarm off set point to 38 degrees centigrade. And back over to the amplifier screen, you can see that the set point has changed to 38 degrees centigrade. This is another example of a fault alarm. I'm going to switch off the 50 volt power supply remotely, and you'll see what happens. I switched over to the diagnostic screen, and voila, it shows me what's going on. Amplifier voltage alarm, and the text box at the top shows me 0 volts. So I'll switch it back on and we'll be good to go. Okay, finally, as promised, here are some echoes on 6 centimeters. Okay, that wraps it up for this project. This went on for a lot longer than I expected. I want to have a special thanks to Hans and Ingolf for helping me out with the amplifier. Without their assistance, that could have never have been accomplished. 73 from Victor Echo 6, Bravo, Golf Tango again.